Okay, and welcome back. We are going to look at 11.3 to 11.5 cube roots. Let's check it out. So we're going to start the conversation by talking about perfect cubes, right? Now, the interesting thing that we learned from last session was that you can actually take the cube root of a negative number. So for instance, when we saw something like the cube root of -8, we said that that was equal to -2. We knew that because -2 times -2 times -2 gave us -8, right? So we were totally comfortable with that. It's very, very helpful up front to recognize perfect cubes. So this is why I have this list written out for you in case you ever wanted to look back. We also learned how to take the cube root of a number using our calculator. As a refresher, we could do the following. You could type in the number 3, then you'll press second, and then the caret key, because above the caret is the xth root. And so this says you're taking the cube root of a number. Let's type in -8. And there you have your cube root of -8 is -2. So it's really nice. You can do this easily in your calculator. The other thing that we learned is that when you have a base under the radical, you can essentially rewrite it as the radicand raised to the fractional power, where you have your power over root. So in this case, it's the same as saying, well, -8 raised to the 1/3, power over root. We learned that. And this is what's going to give us our -2 again. These mean the same thing. They're just radical form, exponential form. Good. Now, in terms of variables, the perfect cubes are very easy, right? Because look at these numbers, 3, 6, 9, 12, 15, 18, 21, 24, right? You can continue to list all of the perfect cubes because every power is divisible by 3. Or another way to think about it, every power is a multiple of 3. So let's check this out. For instance, let's say we have the cube root of x to the 12, right? I don't want you to overthink this. I want you to say, if you're looking for the cube root of x to the 12th, you're simply going to, no worries, Melina, thank you for telling me. You're simply going to take your power, divide by the root, because 3 goes into 12. Yes, exactly. So 12 divided by 3 is 4. That literally is another way to rewrite this expression, power over root, but you're never going to leave your fraction in non-lowest terms. You're always going to reduce that. What will we get from our second expression? This is a cube root of x to the 21st power.
Would it be 7?
Yes. So the expression itself would be x to the 7th. So make sure that you're saying the base and then with that power. Let's do it again. Take the cube root of 27, x to the 9th, y to the 18th. What do you got?
Is it x to the 3rd and y to the 6th?
Good. And now we also have to take the cube root of 27. What times itself again gives you 27?
3.
Perfect. And you're done. Is that making sense? With your variables, you simply divide your powers, right? You divide the power by the root, power over root. I like rewriting it this way. So power over root, this is the same as radical expression. So radical expression, exponential expression. I like using P and R because it's power over root, and roots are in the ground. So that should make sense. Now, in terms of simplifying square roots, it's not going to be as easy as this, but I will tell you that in this class, you're not going to see a bunch of these. It's not like, you know, we're trying to really dive in to see how you deal with cube roots. Like, it's not a huge topic in this class. So I may actually skip a couple pages because it's really not a topic that you're going to see often on your final, and it's not really something that you'll see terribly in college algebra. So I may skip a couple pages because it's a little bit of overkill. Okay, so we're going to understand how to simplify cube roots. Recall that, let me show you just simplifying square roots real quick so that we have a reminder. Here we go. This is simple. So remember when we had square root of 18, we said, let's break that down into a perfect square times the other factor. So we said, when we look at 18, we say 9 times 2 is 18, where 9 is our perfect square. So the square root of 9 is simply 3, and you're left with the square root of 2, and that stays. The idea here with cube roots is the exact same. So let's check this out. I'm going to turn the page. And obviously, we're going to start off nice and easy. We know that the cube root of -8 is, what's the answer here? Phil, what do you get? Cube root of -8.
-2.
Yeah, score, -2. We're done, right? No big deal. Cube root of 48. Is 48 a perfect cube? Take a look at your list. Nope, it's somewhere in between. What perfect cube can go into 48? I can't even talk. Shadim, what do you think? What perfect cube can divide evenly into 48? Ooh, you're on mute.
4.
Well, 4 is not a perfect cube, but you have the right idea. If you look at one of these numbers, does any of these divide evenly into 48?
Yes, 8.
Yes. So check this out. You just said that 8, which is a perfect cube, divides evenly into 48. We know that 8 times what gives us 48? 8 times 6. So I'm going to highlight the 8. I like highlighting. I feel like it helps us to kind of make the connection. We recognize that we highlighted 8 because it's a perfect cube. The cube root of 8 is 2. And you can't take the cube root of 6, so it stays. And you're done. That's it. It's literally the exact same process for square roots. Take a look at the cube root of -54. Does anyone see which perfect cube divides evenly into -54? You can use your calculators, check it out, see what number goes in there. I mean, I'm not a human calculator either. I would definitely punch this in and see what I was getting.
27.
27, interesting. Now, because it's a -54, we're also going to say the perfect cube is -27. We're going to keep the negative with the actual perfect cube. So, perfect cube, you said -27. So -27 times what gives us -54?
2.
Yeah, so let's highlight the -27. That's our perfect cube. And when we take the cube root of -27, we get -3. Don't forget that you're still left with the cube root of 2. That's all we have to do for these. Take a moment to try part D on your own, everyone. Cube root of 135. Feel free to use your calculator. See what numbers divide into 135 and see if you can find that perfect cube. Okay, Nung, what are you finding? What is the perfect cube that divides evenly into 135?
27.
Yes, 27 times what gives you 135?
5.
Perfect. Let's highlight our perfect cube. There it is. The cube root of 27. At this point, you all know it's going to be 3. You're going to see these so often that you're just going to have these memorized. Very nice. Everyone, take a look at the next one, 128. Don't say it out loud. I'll call on you. Give this a second. You may need to punch this into your calculator to figure out what that perfect cube is. Okay. So let's take a look. Who has it?
8 times 16.
8 times 16. Now that's actually great. I like that. So when you think about that, yes, 8 is definitely a perfect cube that goes into 128. The only issue is when you said
64.
times 16, doesn't 16 have another 8 in it? Right? So that means we can go bigger. If 8 and 16 make 128, but 16 has 8 in it, then what's 8 times 8? 64. Try to divide 128 by 64, and you'll see it goes evenly. So let's take a look. 64 is actually our largest perfect cube factor. And then when we take 128 and we divide by 64, we get 2. So we want to look for the highest. 8 does work, but you'll end up having to simplify more. So you always want to look for the highest. So the perfect cube of 64 is?
8.
Not 8. Remember, we're looking for the cube root of 64. What's the cube root of 64? 8's too big. If we do 8 to the third, we end up with 512.
4.
4, yes. 4 to the third power, that's what gives us the 64. So the cube root of 64 is 4. Very nice. Go ahead and try the last one. What do you think of the last one?
Isn't it just 10?
Is 10 a perfect cube though? Is 3 a perfect cube?
Undefined?
It's actually, this isn't undefined, but this is actually simplified all the way.
Oh, okay.
Good. This is simplified all the way. We actually cannot break down the cube root of 30. There are no factors that divide into 30 that would, no perfect cube factors that would divide into 30 that would let us reduce. Okay. Beautiful. Okay. Now, the reason I have this here is because I kind of want to demonstrate what happens, although I think this may be kind of confusing. So what I'm going to do is I'm just going to talk through this really quickly, but I don't want you to overthink these statements. So check this out. X to the 3n is a perfect cube, right? Because 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9. All of these end up being multiples of 3. But if we take the multiples of 3 and we add 1, then it's not a perfect cube anymore. So think of it like this. 3 times 2 is 6 plus 1 is 7. X to the 7th, that's not a perfect cube, right? Because essentially what this ends up breaking down into is x to the 3n times x to the first power, right? Product rule, keep the base, add the powers. This is a hint towards what we had to do when we simplified square roots. When we had variables and square roots, sometimes we had to break it up. We had to break up the variable itself. So as a refresher, let me find something that's very clear and would help. Let's look at, we've done this like so many times. Here we go. Take a look at page 13. Let's look at part F. This is super, super clear. When we had this square root of w to the 9th, we knew that 2 couldn't go into 9, but we knew that 2 could go into 8. So just 1 less. So what we ended up doing was we ended up saying, well, 2 can go into 8. So I'll write this as w to the 8th times w to the 1st because there was 1 left. Here was our perfect square. So the square root of w to the 8th is 8 divided by 2, which is 4. Okay, and we were left with the square root of w. The idea for perfect squares doesn't change. It's the exact same idea. The issue with this is that sometimes you have to take 2 of them away and not just 1. Okay, let me show you. First off, the cube root of y to the 12th, this is a perfect cube, right? So essentially 12 is a multiple of 3, 12 divided by 3 is 4. So our first answer is simply y to the 4th. Notice you don't need a cube root anymore because you're actually using it. What was the analogy I used in class when I talked about applying the square root and not taking it back and doing it again? Do you remember from the video what analogy I used? As a hint, someone will call you a cheater if you do this.
The Uno.
Yes, the Uno, the wild card. So it's like you're playing Uno, you got a wild card, you put it down, you're like yellow, and then as the person's picking, you put the wild back in your hand. People are going to look at you like you're crazy. Like, what are you doing? Why are you playing that way? Same idea here. If you use the square root or the cube root, don't put it back in your hand. That doesn't make any sense. Don't rewrite it on the paper. If you use it, it's gone. I don't know how many times I've seen this where a student will apply it and then put it back and then apply it again and then put it back. And I'm like, you're cheating. You're cheating. You're using your wild card way too many times. I'm not going to play Uno with you, right? So keep that in mind. If you use it, it's gone, right? But if you're breaking up a quantity, you're applying it to that perfect cube or the perfect square, and then it stays on the other non-perfect cube or non-perfect square, just like we've seen many, many times before. Thank you, James. That was perfect. Okay, take a look at this one. Can we take the cube root of z to the 63rd power? We can, definitely. What does this become? Shout it out. Don't overthink it. What are you going to do with the power and the root?
21.
21, score. But Shane, you mean z to the 21st, right?
Yes.
Beautiful. Can we take the cube root of x to the 5th as is, just like that?
No.
No. Okay, perfect. So here's what we have to do. Now we break it up. If this were a 3, I could do it, but it's a 5. So what we have to say to ourselves is we can break this up as x to the 3rd, right? Because if it were a 3, I could take the cube root, but that leaves you with 2 more left over, and that's not a big deal. Remember, all we're trying to do is simplify. So if we take the cube root of x to the 3rd, Tiana, what does that leave us with? What's the cube root of x to the 3rd?
I am not sure.
Well, what do you do with these powers? The power and the root.
That will be 1.
Yes, it would be 1. All you have to do is divide them. 3 divided by 3, that's 1. And you're left with the cube root of x to the 2nd power. How we got 21 is because I did 63 divided by 3. Remember, in exponential form, that's the same as power over root. Y, cube root of y to the 12th, 12 divided by 3, it's 4, power over root. Same thing. Let's check this one out. The cube root of w to the 7th. Well, if this were a 6, I could take the cube root, but it's a 7, so let's rewrite it. If it were a 6, that would be ideal, which means we're left with 1 remaining. Perfect. Summer, when you take the cube root of w to the 6th, what are you left with?
Q?
Yes, w to the 2nd power. Good. W to the 2nd power, and then a cube root of w to the 1st. Good. All right, now you all guide me. Would someone volunteer to tell me how I would simplify this first one? Shane.
So take out the 2 of that. So you got cube root of x to the 12th times x to the 2nd.
Yes, perfect. Shane, can I just dissect what you just did there?
Yeah.
Notice that the highest multiple of 3 that he could take out was 12. So if he removed 2 of them, he was left with a perfect triple, which is exactly what he's looking for. Keep going.
Then you're gonna have x to the 4th to the cubed times cubed root of x squared.
Yes. Also notice Shane says x to the 4th times cube root of x to the 2nd power. Yes, that is the operation that connects them. Thank you so much for including that in the solution. Shane, that was perfect. Who would like to do part F? Part F, someone else. Don't be shy. Jose, you want to take part F?
Let's see.
I like this. You're like, oh, okay. Start with x to the 4th. How would you break this down?
Can we take like x to the 3rd, then x to the 1st?
Yes, beautiful. What about y to the 11th?
Hmm, mm. Can we do it like y to the 6th and y to the 5th?
We can go higher than 6. What's another multiple of 3 that's
9?
smaller
9?
than 9? Yes. Y to the 9th, and that leaves you with y to the 2nd. Good. Now, let me highlight the perfect cubes. Okay, finish this off. Jose, what's the cube root of x to the 3rd?
That will be 1.
Good. X to the 1st. Keep the base there. Okay, so x to the 1st power. What's the
First.
cube root of y to the 9th?
Y 3rd.
Yes, and then we have to write out what's left over. So we have the cube root of these 2 bases exactly as you see them. Perfect. Jose, thank you so much for playing. That was awesome. Very, very cool. Who would like to take part G? Hopefully you're starting to build a little bit of confidence, so you're not too worried about this. Who can take part G? So not Shane, not Jose, someone else. Phil.
I'll give it a shot.
Cool.
So I put 8 under the, I don't know any of the, what to call anything.
The cube root.
8, I'm assuming that 8 stays under the square root sign.
Or the cube root, yes.
Yeah, sorry, cube root, see. And then x to the 13th power would turn into x to the 12th. And then x to the power of 1.
Yes, so let me highlight the perfect cubes here. 8's a perfect cube, x to the 12th is a perfect cube. Okay, so how would you write your answer then?
And then I would have x to the power of 4 on the outside, cubed root.
What's this one?
Oh,
What's cube root of 8?
oh, shoot. I got to write it so I can.
Yeah, what times itself again gives you 8?
Oh, 2.
Yes. So I highlighted both of these because they were both perfect cubes, which means they're both going to be outside of the cube root.
Got it.
And then all that's left under the cube root is that x to the 1st.
Okay.
Beautiful, Phil. Thank you so much.
Yeah, thanks.
It's different when you actually partake, right? It's like, okay, let me dive in and see what happens.
Yeah.
Beautiful thing about this experience, everyone, is that we're in this together. I don't want you to feel shy or nervous or anything. We're literally doing this together. There's no judgment here. This is the first time you're doing stuff like this. Why would I judge you? That's crazy. Okay, so don't be shy about this. Try your hand. Let's see what happens. Part H. Who would like to try part H? So not Shane, not Jose, not Phil, someone else. Don't be nervous. And I'm going to partner with you in this process. James, you want to try this with me?
No, I haven't really figured it out yet. It's just vague. I'd really rather not. Well,
I could call on someone else if you'd like.
well, Professor, I haven't quite figured out like what I'm doing here. I'm not completely lost. It's just,
Okay. Would you entertain working with me?
sure. I don't.
Okay. Okay, cool. So here's what I would do, James. If I look at a problem like this and I wanted to figure out like what the perfect cube is that goes into, for instance, 72. We know 72 is not a perfect cube. It's not on our list. So what I would start off doing is I would look to see if, like, for instance, 27 goes into 72 or 8 goes into 72, that kind of thing. So if I take 72, let's divide it by 27, just out of curiosity. Okay, that definitely doesn't go in, and we probably knew that. But let's divide it by 8 and see what happens. Okay, 8 is a perfect cube, and that does go into 72 9 times. So when I think about breaking down a value like this, I start with each base separately. So let's do this. So I know that 8 times 9 gives me 72. Where the cube root of 8, I can actually evaluate. Like, James, what is the cube root of 8?
It's 2.
Yeah, exactly. So I'm just going to hold that there for a moment. I'll come back to that. Now let's look at x to the 21st. Do you see how this power is a multiple of 3? So if I took x to the 21st and I took the cube root of it, what would that leave me with?
See, I'm trying to connect the dots. I know 7 times 3 is 21.
There you go. There you go. You just said it. 7. You just said it.
Okay, yeah, okay.
Yes. What James is noticing here right now is that when we evaluate the cube root, what's actually happening is we're taking the power and we're dividing it by the root. So you said 3 goes into 21 7 times. That's because in your gut, you know the cube root of x to the 21st is going to be x to the 7th, because you're just dividing power divided by root. But now, and I will write that in a second. I just want to simplify everything. What about this y to the 31st? 31 is not divisible by 3, right?
Mhm.
But how high can we get? What's the highest multiple of 3 that's smaller than 31?
9.
No, go higher, go higher. We're looking for a multiple of 3. As high as you can get it. Start from 31 and then go backwards. Can 3 go into 30?
10.
Exactly. Okay. So 3 can go into 30. So what we're going to do is we're going to break this y to the 31st down. We're not going to take the cube root yet. We're just breaking it down. You just said to me that if we had a y to the 30th, we can take the cube root of this, because you said it divides evenly and it becomes a 10. But remember, we still have a y to the 1st. That's still remaining. So check this out. 8 times 9, 72. X to the 21st, we didn't touch because it's a multiple of 3. Y to the 30th times y to the 1st is y to the 31st. So everything is exactly the same. All we did was rewrite it so that I can highlight each of these perfect cubes. This is going to be the part that I hope will be incredibly helpful, to break it down first so that you have that visual. And then once every single base is broken down, if necessary, then you take the actual cube root. Okay, let's go through this again. Cube root of 8.
2.
Cube root of x to the 21st.
7.
Good, and make sure you keep the base. So x to the 7, keep that variable there. Cube root of y to the 30th.
10.
Good.
Y to the 10.
Yes, perfect. And now everything that's not highlighted stays. So cube root of 9y to the first. These just stay there because we can't do anything with them. Remember, 9 is not it's not a perfect cube. There's nothing times itself that gives you 9. It's a perfect square, but that's besides the point. Our root is 3, not 2. So don't make the mistake of doing, oh, 9 divided by 3 is 3. That's true, but that's not what this says at all. This is not a division problem. This is the cube root function. Okay? Thank you, James, so much for trying your hand out on this one. That was awesome.
You're welcome.
Let's turn the page. Okay. Now, recall when we had a fraction of square roots or square root of a fraction. We thought about the idea of simplifying under the radical sign, like making it one fraction and then simplifying and cleaning up where we could. And then we actually took the square root, or, you know, maybe we had to break it up. Maybe we had to rationalize. That idea doesn't go away with cube roots. It's just a little bit more involved, right? But we know what perfect cubes look like. We also know what perfect cube powers look like for a variable base. So when I show this to you, for instance, like with this first example, I want you to be comfortable with the idea that a fraction of cube roots is the same as the cube root of a fraction. Because we learned last class, a fraction of square roots is the same as a square root of a fraction. Let me show you. It may sound like I'm saying the same thing, but I'm really not. Okay, we have a fraction of cube roots. Well, let's rewrite this. I want to write this as the cube root of a single fraction, because what this will allow me to do is to simplify the fraction. Let's look at my base x. I have x to the fourth over x to the first. How many I have left and where?
X to the third in the numerator.
Yeah. So Phil, you just applied the quotient rule. You said, I easily know that if I have 4 factors of x in the numerator and 1 in the denominator, well, this guy's going to go away and this is going to become a 3, right? I'm just going to start rewriting this. So we have x to the third. Good. Would someone else take a look at those y's? Y to the 10th over y to the negative 2 power. What do you recall from your exponent rules? What's going to happen?
You're not suggesting that the negative 2 gets bumped up
I am totally suggesting that.
to a
Yes.
positive? Okay.
Yes, you're absolutely correct. James is applying the negative exponent rule. And what he's saying is, if you have a base to a negative power in the denominator, well, in order to make that power positive, you're going to have to move that to the numerator, and this becomes y to the positive 2. So now I have y to the 10th times y to the second power. When I simplify this, what does it give me? Put these together.
Y 12.
Yes, y to the 12th power. Beautiful. Now that I've cleaned up what's in our fraction PEMDAS, right? Think about parentheses. The interesting thing about this piece is that my cube root acts like a parentheses because it's housing information. Parentheses house information. So do square roots, so do cube roots, so do radicals. So take a look at what we have left. We have a cube root of x to the third, y to the 12th. These are both perfect cubes. Who can provide to me the final answer? Simplify this for me. What's my answer?
X,
X to the first.
and then y to the fourth.
Cool. Y to the fourth. You're done. X to the first, y to the fourth. You've evaluated that cube root. Very nice. Very nice. I like what I'm seeing. take a moment, each one of you, take a look at part B, simplify the fraction first. I want you to simplify the fraction first. That's all. Leave the cube root there. Okay, Summer. Leave the cube root there, just simplify the fraction.
27. No,
Good.
wait.
27 stays,
X to the 6th.
x to the 6th.
And then on the bottom, 64. Y 15.
Yes, perfect. All Shane did was apply the quotient rule, x to the 7th over x to the 1st, you're left with x to the 6th in the numerator. Y to the 2nd over y to the 17th, you're left with y to the 15th in the denominator. Cool. Guess what, guys? Every single base is a perfect cube. So Shane simplified this for us. Someone else bring this home. What is the cube root of each of those pieces? Someone else bring this home.
9.
Ooh, careful. 9 times 9 times 9 is huge. It's 729. You're thinking smaller. What times what gives you 27?
3.
3. Good. So you wanted 3. Keep going.
Over
What else
4.
is in the numerator?
Uh, um,
X to the 2nd.
Yeah, x to the 2nd. You said there was a 4 in the denominator? Absolutely.
And Y to the 5th.
Yes, perfect. 6 divided by 3, 2. 15 divided by 3, 5. Cool. When you take the cube root of a numeric piece, that's very different from taking the cube root of a variable piece. They act differently. They have different rules. All right. Good. Remember, if you have any questions at all, please don't hesitate to ask. Okay. For part C, the first thing we're going to do, and I'll do this with you, the first thing we're going to do is we're going to simplify what is under the cube root. Notice we have a 10 and a 16. So immediately I'm going to say, well, I can divide out a common factor. That common factor is 2. Let's divide out a 2 from the 10 and the 16. That leaves me with a 5, and that leaves me with an 8. Now I have x to the 6th and I have x to the 4th. Well, if I use a quotient rule, I subtract the powers, leave it where it's heaviest. So I'm going to have x to the 2nd in my numerator. Notice I still have a z to the 7th. That's not going to go away because I don't have any other z's. And then I have a y to the 9th, and that's in the denominator. So now I want to take the cube root of all of this. I have some perfect cubes right off the bat. Can someone identify what those perfect cubes are without manipulating anything? Which ones are my perfect cubes?
8.
8. And?
X to the 2nd, I think, maybe.
Well, right, x to the 2nd is too small because it's got to be 3 or
Y to the 9. maybe?
yes, 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 perfect. As it stands, those are my perfect cubes. But check out this sneaky guy right here. This sneaky, sneaky, sneaky. Z to the 7th. Can't this be rewritten? What can this become?
6 and 1.
Yes, it can. So this should actually be rewritten as z to the 6th times z to the 1st power. And I'm just going to extend this so that you can see what's happening. Let's highlight the z to the 6th. Okay, piece by piece. First off, cube root of 8. Shout it out.
2.
Where is it?
At the bottom.
Yes, it is. It's got to stay there. Good. Cube root of y to the 9th. What is it?
3.
What is it?
Y to the
Y to the third. Good. Where?
denominator.
Exactly. Okay, cool. Very nice. We can't do any of these, right? But we can do this one. What's the cube root of z to the 6th?
2.
What is it?
The Z.
Yes. Z to the 2nd. Where is it?
Numerator.
Yes,
Numerator.
it is. Z to the 2nd up top. All of the rest of this stuff, the 5, the x squared, the z to the 1st, we cannot break that down anymore. So in my numerator, I'm going to leave 5 x squared z to the 1st all under the cube root sign. And now we're done.
So 9 is a perfect cube.
Yes, because it's a power. So think of this as like being able to divide this power by the root. Power divided by root. Always say that, James, that's going to be huge. Always say power divided by root. Because you can look at this power of 9.
Yeah.
9 can be divisible. 9 is divisible by 3. You're golden. It's a perfect cube, but only because it's a power.
Okay.
And another way to look at this is consider your perfect cubes here, right? X to the 3rd, X to the 6th, X to the 9, 12, 15, 18, 21, 24, 27, 30, 33. All of those are perfect cubes because they have a variable base and we're referring to their power. Another way to think about this is cube root of y to the 9th. When we rewrite it in exponential form, it's power over root. Power over root, okay? Which is what tells us, oh, this is just y to the 3rd. There are a lot of different ways to kind of navigate problems like this. And sometimes it's helpful to look at it in different ways too. So just remember, James, your numeric pieces work very differently from your variable pieces. With your variable pieces, it's always power then the root, power then the root.
Yeah, I'm trying to distinguish the two.
Yes. Just treat them completely separately, literally completely separately. Like it's a little weird, but the second you have a base with a power, open up this in your mind, power divided by root. Okay. And I think you're going to be in really good shape. Just keep saying that, power over root, power over root, power over root. Good. That was very nice. So with the first one, we had to make it into one fraction and then we simplified everything. These were already provided to you in a nice fashion. So we were able to simplify before we actually applied the cube roots anywhere. Okay. For this last problem, we really couldn't go any further. The 5x to the 2nd z to the 1st, that's going to stay under your cube root, but everything else was able to be simplified. Good. Now, when you add or subtract cube roots, that's the same thing with when we added or subtracted square roots, which is the same thing of when we added or subtracted variables. Okay, so check this out. We have 2x plus 4 cube root of x minus 6 plus 5 cube root of x. I want you to notice that I have like terms. The positive 4 cube root of x and the positive 5 cube root of x are like terms. They can't be simplified. They're as simplified as it gets. What would the power have to be here if it were able to be simplified? What should the power be here if we could actually simplify? What should that power be?
Three.
Or more, or more. You're right, 3 or more. 3, 4, 5, 6, 7, 8, 9, all the way to infinity. If that power were higher than 3 or more, then we can simplify. But this is less than 3, so it stays. Good. They're like terms, so we want to put these together. What I would recommend is maybe putting these at the end. So for instance, we can write 2x minus 6 and then 4 cube roots of x plus 5 cube roots of x is 9 cube roots of x, and you're done. You're just saying how many are there. Oh, there are 9 of them. Okay. I don't want you to overthink it. It's literally like what we did with variables. So like, for instance, if I had 2m plus 4p minus 6 plus 5p, well, you would say the p's go together. You would say 2m, and then you'd say these give you 9p, and then you'd subtract the 6. Now, I do want to point out to you that I personally like to write the radicals at the end, because I've seen the mistake of putting minus 6 here, and then somebody accidentally writes it under the radical. And that's a huge problem because it's a different term. So just be careful with that. Okay, take a look at part B. Cube root of 8. This is
2.
2. That was a perfect cube, so we actually simplified that. Cube root of 54, can this be broken down? If so, into what? Give me a perfect cube and its other factor. Give me a perfect cube and its other factor.
27.
Yeah, 27 times?
2.
Yeah, score. What's a cube root of 27?
2.
Because that would be 8.
3.
3, score. Good, I love the teamwork. That's really important. So we're gonna replace cube root of 54 with 3 woohoo! 3 cube root of 2. This is gonna replace cube root of 54. So plus 3 cube root of 2. Sorry I wrote that so tiny. I have no idea why I wrote it so small. Minus 7 cube root of 2. That's much better. Don't know what happened to this guy. So now we have our like terms. Our like terms are positive 3 cube root of 2 minus 7 cube root of 2. What will that leave you with? 2. How many would you be left with?
-4
Cool.
over cube root of 2.
Yes, perfect. It's kind of a tongue twister, isn't it? It's like messing with me. So 2 minus 4 cube root of 2, done, perfect. Because 3 minus 7 is -4. And that's it. Finito, you're done. You don't go further than that. That's all. That's literally it. Very, very cool. This page below is exactly the same. We can go through this process once more. Feel like this is starting to be overkill, but maybe it's good practice. 16, break it down. Perfect cube and the other factor. What do you got? Let's do this faster. 16, break it down. Down.
4.
Careful. It's not the square root of 16. What times what gives you 16? One of which is a perfect cube.
8 times 2.
Yes, 8 times 2. Remember, we're looking for perfect cubes. If it helps, think of these. Let's see, 8, 27, 64, 125, 216. Those are perfect cubes. And obviously they're negatives. Okay, very nice. We have x to the 4th. How should we break down x to the 4th?
Make it x to the 3rd and x to the 1st.
Yeah, x to the 3rd, x to the 1st. Very nice. Someone else, how do we break down y to the 23rd? Yes. Yes, awesome. Y to the 21st, y to the 2nd. Beautiful. Beautiful. So I'm hoping you went backwards. I'm hoping you said, well, 23 is not divisible by 3. Neither is 22, but 21 is. 21 will work. Start from the highest and go backwards. All right, perfect. Cube root of 8 is 2. Cube root of x to the third, 3 divided by 3, that's x to the first power. Cube root of y to the 21st, 21 divided by 3 is 7, so it's y to the 7th power. Then you're going to write down that you have the cube root of everything that's not highlighted. Hopefully the highlighting helps a lot. And there's your final answer. Cool. For part B, I would actually multiply them first. That's what I would do if I were you. I'd multiply these two first and then figure out if you can simplify. So for instance, we would take the cube root and we'd say, okay, well, 4 times 5 is 20. X times x is x squared. Y to the second times y to the second is y to the fourth. I'd look at 20 and immediately I know that I don't have any perfect cubes that can go into 20. 8 can't go into 20, and obviously 1 is not going to help us. With an x to the second power earlier, I asked what should the power be to simplify, and Phil said 3 or more. This is a 2, so you know that we can't break this down anymore, right? Okay, perfect. Y to the fourth ends up being the exact same thing that we saw here with x to the fourth. So we can actually break that first one, or that y down. So we have 20x to the second, y to the fourth breaks down into y to the third times y to the first. There's our only perfect cube. That was literally the only one we had in the entire problem, which is okay. It doesn't have to be that you find one every single time. So cube root of y to the third is y to the first, and guess what? Everything else stays. So 20x squared y to the first, done. That's it. Everything else will stay because you cannot simplify anything else. Take a couple moments to play around with part C. Remember, multiply them first and then simplify. Take a couple minutes. When you think you have your answer, type done in the chat. Because yeah, typing in cube root is going to be annoying. So just type done when you think you have your answer. Okay, so the first thing that you should do, and this is something I would do too, is I would just multiply it. So 4 times 16, that's 64. A to the second times a to the second, that's a to the fourth. B to the second times b to the fourth is b to the sixth. Remember, keep the base, add the powers. Okay, so right away, I noticed that, oh, 64 is a perfect cube. That's awesome. B to the sixth is a perfect cube. A to the fourth, we can easily fix this. So for the sake of just making sure we understand, I'm just going to rewrite it. Who cares, right? It only takes me like an extra second. So a to the fourth breaks down into a to the third times a to the first. And again, let me highlight my perfect cubes. This one, and now the last one. So now we just evaluate each perfect cube. Thank you, Zach. That's beautiful. Cube root of 64 is 4. Cube root of a to the third is a to the first. Cube root of b to the sixth is b to the second. And then we're left with cube root of a to the first, and we're done. Nice. Very, 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 very nice. Okay. Be very careful here with your evaluation. If the whole cube root thing is like throwing you off with your numerical part, just like notice that your base is 64. So if you take 64 and you raise it to the 1 divided by 3, right? Because that's exponential form, it'll tell you that it's going to be 4. That's the same as cube root of 64. 64 to the 1/3 is the same as cube root of 64. And that'll just show you that it's 4. All right. The other thing you could do is just write above your perfect cubes what they actually become. So like, for instance, this is 2. This is 3. Give yourself like a little cheat sheet. This is 5. This is 6, right? Just give yourself a cheat sheet so that you know. Beautiful. Are there any questions on anything we've done so far? Okay, I'm gonna leave this one for you to play around with, but I actually want to show part B. Not that it's overly complicated, but we haven't really done one with a coefficient. But I'm hoping that that's not going to throw you off because nothing changes, right? For instance, you're still going to multiply your cube roots together. So let's look at part B. So I'll leave A for you to play around with. This is for you. You enjoy. Okay. Uh-huh.
After part B, can we take 5?
Yes, absolutely. Absolutely. So let's multiply these guys. So we've got 5. We know that cube root of 6x to the second times cube root of 9x to the fifth gives us the cube root of 54x to the seventh. So 54x to the seventh. Once we put those together, now let's look at each base. We've seen 54 before. We know that 27 times 2 gives us 54. So I'm just going to rewrite this. Don't forget there's a 5 there. So we have 27 times 2. That's what gives us 54. And 27 is that perfect cube. What does x to the 7th break down into?
Excuse me, I'm sorry. X 6?
Yes. Perfect. X to the 6th and x to the 1st. Yes, that's perfect. You know, 7 is not divisible by 3, but 6 is. So that's why we write 6, and then we say, oh, okay, there's 1 left over. Highlight that x to the 6th. And now check this out. We still have a 5. Like Shane had mentioned maybe almost an hour ago, this is 5 times everything, right? So 5 times the cube root of blah, 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 blah. So when we take the cube root of 27, we know that it's 3. But this doesn't become 53. That's weird. It becomes 5 times 3. The cube root of x to the 6th is x to the 2nd power. So it becomes 5 times 3x squared. And you still have the cube root of 2x to the 1st. This you would never leave as is. 5 times 3x squared is 15x squared. And there is your final answer. Okay, you wouldn't just like leave that lingering. That's not cool. You can actually multiply these. It's not a big deal. Beautiful. All right. Okay, so let's check this out. So now we're going to learn how to rationalize with cube roots. This is not a big deal. Actually, I want to show you what we did with rationalizing square roots. As a reminder, as a refresher, check this out. Hi, puppy. Okay, so for instance, the issue with fractions and having radicals is that if you have a radical in the denominator, that's a big no. That's a big no. Can't do it. So what we ended up doing here is when we saw that radical in the denominator, because this was a square root, all we had to do was rationalize by multiplying by whatever that value was. So square root over square root of 2 over square root of 2. We learned that the numerator is simply x times square root of 2, which is just x squared of 2. And then in the denominator, we had 3 times, well, square root of 2 times square root of 2 is 2, right? Because square root of 2 times square root of 2 is square root of 4, square root of 4 is 2. So we made our life easy by saying, well, I know this, square root of 2 times square root of 2 is 2. Just like square root of 3y times square root of 3y is 3y, right? We didn't overcomplicate that. Once you actually did the math, that was your final answer. So we rationalized by multiplying by that radical, the square root of 2, by itself, essentially. Now this worked out because we know that square root of 2 times square root of 2 is simply 2. Now here's the difference. When we look at, one second, I just want to make sure I put this page back. When we take a look at something like this, where we have a cube root, I want you to consider the following. We know that because it's the cube root, you need 3 of them to have your radicand. So for instance, and I want you to hear me, cube root of 2 times cube root of 2 times cube root of 2 is 2. That's the difference. Square root of 2 times square root of 2 is 2. When you think of square root of 2, or excuse me, square root of 2 times square root of 2, that's like saying square root of 2 squared, which is why the square and the square root cancel each other out. But when we're dealing with cube roots, because the root is 3, you're going to need 3 of them to cancel out, right? It's like a power of 3 and the cube root, they eliminate each other. You know this because when we took the cube root of x to the third, you said it was x to the first because they canceled each other out. So when we rationalize, we just have to remember if the root is 3, we need 3 of them. If the root is 2, you need 2 of them. That's it. So let me show you. To clean this up, to rationalize this, because the problem is no radicals in the denominator. That's an issue. So we want to rationalize by taking that cube root of 2 and multiplying it by itself 2 more times. I don't know why I'm struggling to write that. I'm struggling hardcore to write cube root of 2. It's stupid. So now that there are 3 of them, 1, 2, 3, well, the cube root of 2 times itself again is simply 2. If you do not buy that, well, let me show you. Take a look up here. Actually, let's take a look up here. Cube root of c times cube root of c times cube root of c is the same as cube root of c to the third, right? Because c times c times c is c to the third. Cube root of c to the third is c. Take a look at this guy. Cube root of 4m times itself again. 4 times 4 times 4 is 64. M times m times m is m to the third. And then the cube root of 64m to the third is 4m. You see, 3 of them gives you the radicand. 3 of them gives you the radicand. So I just wanted to show you that so that you can be pretty confident. We clean up the numerator by saying, well, I have a 5, but I also have a cube root of, and then we see 2 times 2, which is 4. We cannot simplify that. 4 is not a perfect cube, nor does it have a perfect cube factor other than 1. And that's not going to be helpful to us. Okay. Let's look at B. The issue with B is the denominator. So I actually want to rationalize first before I simplify what's going on up top. I think if you're looking at the numerator, you're probably already thinking, well, there's a perfect cube factor, it's 8. And this one can break down too. And we'll do that, I promise. We'll do that, just not yet. Let's start by rationalizing. So we have cube root of x to this, cube root of k to the second. And because it's a cube root, we need to do that one more time. K to the second, k to the second. So that there's 3 of them in the denominator. Because if you have 3 of them, then you're left with simply k to the second. Okay. Cube root of k squared times itself leaves you with just k squared. Now I will put everything in the numerator together under one cube root sign, and then we'll figure out, how to simplify it. So we have cube root of, we've got 16 m to the 4th, k to the 4th. So 16 m to the 4th, k to the 4th. What I may want to do now is just focus on the numerator, and then I'll rewrite my answer. So I just want to focus on this part. So the cube root, I like to do a lot of side work so that it doesn't clutter up the space that I'm using to actually write my answer. We look at 16, we're looking for a perfect cube. That's going to be 8. So 8 times 2 is 16. I'm going to go ahead and highlight 8. M to the 4th, we did this a bunch of times already. That's going to be m to the 3rd and m to the 1st, right? Because we're looking for a perfect cube. And then k to the 4th, well, that breaks down to k to the 3rd and k to the 1st. Again, same idea. We've seen this a bunch of times already. Cool. So I'm going to go ahead and write down what this becomes. So cube root of 8 is 2. Cube root of m to the third is m to the first. Cube root of k to the third is k to the first. And we're left with the cube root of 2mk. 2mk. And you can write each of those to the first power if you would like. Please stop me if I'm moving too fast or if something doesn't make sense. I'd be happy to break it down further. Okay, please stop me if something's not clear. So what we want to do now is we want to rewrite the problem. What I've just done is I've taken the numerator and I've simplified this radical so that I get this particular expression. But remember, this is all over k squared. So let's rewrite what I have. I have 2m to the first, k to the first, cube root of 2mk all over k squared. Do you notice anything?
Outside and inside the square root of this.
Okay, they definitely are, which is kind of neat. What else do you notice? Think in terms of answering this question. Can I simplify more?
You can move the.
And get rid of the.
Yes, the k, we can get rid of the k's. Check it out right here. We have k to the first over k to the second power. They have the same base. We're going to apply the quotient rule. We're going to subtract and leave it where it's heaviest. So guess what? My final answer, see how we simplify that? We divide out that factor of k. My final answer is going to be 2m to the first cube root of 2mk all over k to the first power. Now you're done. Talk to me. Questions, concerns, comments?
I have a question.
Yes, awesome.
When we're doing, so over to the right, when we're doing the 8 times 2 times m to the third times m to the first, why do we do m to the third times m to the first?
So the reason we break down the m to the fourth this way is because we always want to simplify your variable bases whenever the power is more than the index, right? So because this power is 4, we know, okay, well, 3 can't go into 4, but it can go into 3. So we break it down and we say, well, m to the fourth is the same as m to the third times m to the first. Remember, what we're looking for are perfect triples, we're perfect cubes. M to the third can be evaluated under the cube root. That's the same way with k to the fourth. We break it down, k to the third times k to the first. We're looking for perfect cubes. That's how we simplify it. Excellent question. So we're always looking to simplify. Very nice. James, talk to me.
No, I didn't even hear the question. I'm sorry. You explained that. I want to know what was asked.
She just wanted to know, why did we break down m to the fourth? Like, why would we even focus our attention on this? And I was just explaining because that power is greater than the index. That's what tells us we can actually simplify that further. If the power is bigger than the index, you've got to simplify.
Okay.
Beautiful. Beautiful. Take a look at part C. What's so bad about part C? What's the problem area here? What's the problem with this particular example?
Z.
The Z, tell me more. Anything else? What else is down there?
4.
Oh, if it's not super clear what this looks like, I'm going to break this down into a fraction of cube roots because I think that's going to help. This is the same as cube root of x to the second y to the 10th all over the cube root of 4z. That's the problem. We have a radical in the denominator. That's what this fraction says. This is a cube root of a fraction, which is the same as a fraction of cube roots. The problem is the denominator. How do I fix this? What should I do?
Three and one, maybe.
Well, I will break it down soon, but not yet. Well, how do I fix this? What strategy are we going to employ?
4z 3 times.
Yes, okay. The cube root of 4z 3 times, right? There's the first one. We want to do it again. We want to do it again. And remember, that's going to be the same in the numerator, because we want to just multiply by ones. We don't want to multiply by anything other than a 1. Check it out. We've got 1, 2, 3. What's the cube root of 4z times itself again?
4z.
Yes, beautiful. I love it. Isn't it nice? It's so great. Now let's fix the numerator. We've got a lot going on. Let's put it together and see what happens. In the numerator, when we multiply everything, we have the cube root of, you tell me, what do we have?
4z x squared y10.
We have more than that. Take a look at all of them. Put them all together.
Oh, I'm sorry. 16z squared x squared y10.
Yes. Perfect. 16 z squared x squared y10. All of that was in the numerator under the radical. We want to go through the same process we did before. Are there any questions? Are you guys okay with this? X squared y to the 10th, 4z. We're just multiplying all of these. So 4 times 4, 16, z times z squared, and then you still have x squared y to the 10th. We are going to simplify the numerator and see if we can find any perfect cubes. So we're going to do some side work. I'm just going to write side work. Cube root of 16, z to the second, y to the second. Oops, nope. Hold on. Hold on. There we go. I'm at x to the second, y to the 10th. Cool. What's the first thing that breaks down? None. Start us off. What's the first thing that breaks down?
16.
And it breaks
And it'll
down
be
into
8 times 2.
yeah, score. 8 times 2, because she knows that is a perfect cube right there. What's the next thing that breaks down? Which one?
Y.
It does, not the z, not the x. Both of these have powers that are smaller than the root, so you can't do anything with those. So I'm going to leave z squared, I'm going to leave x squared. And Phil, how would you break down the y?
Y to the 9th and y to the 1st.
Yes, beautiful. Y to the 9th and y to the 1st. We know that y to the 9th is a perfect cube. Because remember, power divided by root. So if we simplify this, cube root of 8 is 2. Cube root of y to the 9th is y to the 3rd. And then everything else stays under the cube root. That's 2. And I'm going to put these in alphabetical order. X squared, y to the 1st, z squared. Good. So let's rewrite our problem. In my numerator, I have 2y to the 3rd cube root of 2x squared y to the 1st z squared. My denominator is 4z. Can I simplify further? Am I done?
I think you're done. Because you can't mess with that z in the square root. It's in the square root, right?
I agree. You're totally right. This is trapped. I like that you pointed out. This stuff is trapped. Can't do anything about that. Does anyone see anything else?
The 2 and the 4.
Yes, the
Four
2
and
and the 4. We can divide these out. These are my coefficients. They're not trapped under the cube root, so we can definitely divide these out. We're just essentially simplifying this fraction. So 2 can go into itself once and into 4 twice. That is allowed. So your final answer is y to the 3rd cube root of 2x squared, y to the 1st, z to the 2nd power, all over 2z. Done. Woo! That was a big one. That is a huge problem, but it's manageable. I urge you to do side work. Don't clutter up your page by putting everything cramped together. You're gonna hate life if you do that. Okay, tricks of the trade. That's what I would do. Cool. As a note at the very bottom, a cube root expression is simplified when the following are all true. And this kind of speaks to, Christina, your question earlier. So you'll know that it's simplified if inside the radical, all the exponents are less than the index. So if they're greater, okay, we got to break it down. The constants don't contain any perfect cube factors, right? And then there are no fractions. That's huge. You have to make sure that these 3 things are the case. In terms of the second thing, it's kind of speaking to the whole idea that there are no fractions. So we have to note that the denominators do not have any cube roots. The denominators can't have any radicals. We have to just remember that. If it does, we have to rationalize. Okay. What's that?
What does A mean? What does exponents must be less than the index? What does that mean?
Oh, that means that your powers are less than the index. So for instance, here, actually, let's go to my answer. I know that this is simplified completely because my power is 2, that's smaller than my index. My power is 1, that's smaller than my index. My power is 2, smaller than my index. Index is another way of saying root, like
Okay.
cube root, square root. Those are indices. 3, 2, those are your indices. Because indexes is not really an actual word. a little English, a little English in there. Yeah, we just have to make sure that the powers, if they're smaller than the index, you know you're good. That you can't break it down further. Good. Excellent questions. Now, this is a page I actually don't want to do, but I would like to show you a couple just because I know you could do them. So for instance, what's the 4th root of x to the 20th? You know how to do this.
X to the 5th.
Done. How'd you get x to the 5th? Because what did you do?
20 divided by 4.
Yes, score. Beautiful. What's the 5th root of x to the 30th?
X to the 6.
Yeah, how'd you get that?
You divide 30 by 5.
Okay, perfect. What about part C? What's the 6th root of x to the 24?
Four to the,
4.
oh, x to the
X to the
4th.
Yeah, perfect. X to the 4th. How'd you get that?
Divide.
You just divide 24 divided by 6. Perfect. So I just wanted to prove to you that even if your index, your root is higher than squared or cubed, that you know what to do because the process doesn't change. It doesn't change at all. We'll just do one more. Take a look at the 4th root of x to the 4th, y to the 23rd. You know that 4 can't go into 23. What's smaller than 23 that 4 can go into?
Twenty.
20. So we go through the same process. X to the 4th, we're not going to touch that because that's perfect. And you said 20, right? Which means there are 3 left over. We highlight the perfect quadruples. Yes, I literally said quadruple. The 4th root of x to the 4th, x to the 1st. The 4th root of y to the 20th, y to the 5th. And you're left with the 4th root of y to the 3rd. That's it. So I wanted to prove to you that even if we had a higher order radical, that you know exactly what to do. Okay, how about you do these two? I only want to give you 120 seconds. That's all you need. Take 120 seconds, do parts E and F real fast. That's it. Very, very, very nice. I love it. That's exactly how you would simply break this down. Score. I'm not interested in doing part C, so this is completely up to you. If you want to play around with this, it's not important. You're not going to be tested on something like that, but you can feel free to play around with it. And then when we look at the next page, yeah, if I had a bazooka, I'd aim it at this problem. So we're not going to do this page either. Okay, totally up to you if you'd like to play around with it. This is an incredibly complicated problem and it's incredibly unnecessary for our class. Okay, so totally something you can do if you just want to play around. Let's turn the page. Yes, now we are where we need to be, and that is solving radical equations. I love this because it actually just applies the whole idea of understanding that if you have a square root and you square it, you cancel each other out. If you have a cube root and you cube it, it cancels each other out. So let me just read to you the instructions on how to solve radical equations. Step 1, isolate. So on one side of the equal sign, isolate one radical so that everything else is on the other side. Is. Step 2, eliminate a radical. How you do that is you essentially raise both sides to the power that matches the root on the radical. So if it's a square root, you're going to square both sides. If it's a cube root, you're going to cube both sides. If it's a fourth root, you're going to raise both sides to the fourth power. We won't see those. For step 3, you are going to solve for x. If you still have radicals, you just essentially repeat steps 1 and 2. You keep going until you eliminate all the radicals. And then of course, please, 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 please check your result for any extraneous solutions. It's very possible for that to happen. So let me give you an example. You see here how we have the square root of x is equal to -4. Well, I'm hopeful that you would see this and be like, nope, can't solve this. You can't solve this. Is there any number you can take the square root of and it leaves you with a -4? No. Immediately, I would say no answer. Me personally, if I saw this, I'd be like, nope, no answer. However, if you didn't recognize this and you did square both sides and you found that x was 16, if you tell me that your answer is 16, I'm going to say, did you try plugging it in? If you plugged in 16 into your original problem, the square root of 16 is +4, not -4. So that means 16 would be the extraneous solution. So there would be no answer. You would write no solution. Okay, let's check it out. First off, square root of x is equal to 5. This is possible because 5 is positive. So because I want to solve, I have to think to myself, well, what is the opposite of square root? And you know the opposite of square root is square. So take each term, each side of the problem, put it in parentheses, and go ahead and square each side. The square root of x squared, check out what happens. It's actually really, really cool. The square root and the square cancel each other out just like that. It leaves you with x, and then 5 squared is 25. Double check. Cool, it works. The square root of 25 is 5. I found the answer. What do you think? Not bad, right? So far, you're probably looking at B and being like, this is way different. Yes, that's true. Let me show you how to navigate part B. We want to isolate this term, this 2 square roots of x. So if I want to isolate this term, I'm going to subtract the x, and I'm also going to add the 3. I'm gonna bring both of those over. That leaves me with 2 square roots of x is equal to negative x plus 3. I could divide by 2 as well to get square root of x completely by itself, but I don't really want to do that first. I just want to square both sides now. I want you to be very careful with this. When you square both sides, because you want to eliminate that radical, you want to eliminate that square root, this is how you do it. You must square both sides entirely. Okay? Think about this first. What's 2 square roots of x times 2 square roots of x?
4x squared.
You're close.
4x?
Yes, much better. 4x. If you want, go ahead and write this out here just so you can see it. 2 times 2 is 4. Square root of x times square root of x is x. Okay, now the other side is a binomial raised to the 2nd power. So guess what? We're going to go back to 098 for a second. And we're going to say, well, that means I'm going to have to write it out twice and distribute. So we have negative x times negative x, that's x squared, positive, right? Negative x times 3, that's negative 3x. Negative x, or positive 3 times the negative x is negative 3x. And 3 times 3, both positive, is 9. So this becomes x squared minus 6x plus 9. Excellent. Where would you go from here?
Bring the 4x over, set it equal to 0.
Perfect. We are applying our rules from unit 1 when we were solving by factoring. X squared minus 10x plus 9. What does this factor into?
X and x,
Mm-hmm.
9 and 1.
1 and 9.
Yeah, and give me the signs.
Negative.
Negative 4. Positive 9.
You sure?
Negative 9.
Oh, negative.
Yeah, excellent. X squared, always double check. Negative 9x, negative 1x, that gives us negative 10x, positive 9. Beautiful. What are your solutions? X is equal to?
1 and 9.
Good. Check them both. Okay, check them both. Let's try the 1. So we have 1 plus 2 square roots of 1, which is just 1 times 2 is 2. So 1 plus 2, which is 3, minus 3 is 0. That works. Then check 9. 9 plus 2 times square roots of 9. Well, square roots of 9 is 3. 3 times 2 is 6. So 9 plus 6, right? It's a positive. So 9 plus 6 is 15, minus 3 is not 0. So what that means is we're going to throw the 9 away. Okay? You always have to double check. The 9 does not work. So our answer is going to be the solution set 1. That's the only answer we're going to have for part B. Is everyone doing okay on this? I'm sorry, there's not a lot of room. I'm done talking. You guys go. What do I have to do? You walk me through the whole thing for part C. I'm ready when you are. What should we do for part C?
Well, I mean, you can't square root 5.
Right.
So we can 4.
Can we combine negative 1 and 5x? No, that's different.
Yeah. Take a
Do
look
we
at.
bring x to the other side?
Yes. We're gonna bring X to the other side because of step 1. Isolate. On one side of the equals, isolate the radicals so that everything else is on the other side. Good. Twiggy, don't hit the camera, please. So we have square root of 5x plus 4, as if she understood me, right? I talk to my dogs like that all the time. And then on the right-hand side, we have x minus 4. I'm just going to write it like that. Instead of negative 4 plus x, I prefer to write x minus 4. Okay, you keep going. What's next?
Square root both of them.
You mean square? Yes. Square both sides. Good. What does this become?
Five x plus 4 equals x squared minus 16.
Oh, careful. Don't make that mistake, Shane. It's a tiny mistake, but you've got to do what with that x minus 4 squared?
So it'd be x squared minus 4x.
Ah, yes. I'll write it out so you could see it. Good. Keep going. Shane's not alone. Help him out.
Minus 4x minus plus 16.
Good. Keep working together, guys. What's next?
So then those middle ones will become, so we're combine like terms. So, or bring that, we'll do this all in one thing. So we're gonna bring that 5x and that 4 over, and then we're gonna combine like terms. So we'll have 0 equals x squared, that's easy. 0 equals x squared, minus x squared minus 3 plus 20. Or no, I'm sorry, plus 12.
Good. What about this middle term? That's going to be 13. Good. Be careful. It's going to be minus 13x plus 12. Very nice. Good. Shane did a whole chunk of this.
We'll have
Shane,
x and that. Do you
let's,
want me to finish it at this point?
sure. Okay.
So then we'll have x and x, and our factor's going to be 12 and 1, both negative.
Good.
So then our answers will be positive 12 and positive 1.
Good. Let's check it. Let's punch this in here. So 5 times 12 is 60. 60 plus 4 is 64. Square root of 64 is 8. 8 minus 12. If we take 8 minus 12, we get negative 4. So that actually checks out. So this one looks good so far. We still want to check the 1. So if we plug 1 in, 5 times 1 is 5 plus 4 is 9. Square root of 9 is 3. 3 minus 1 is 2. Doesn't work out. So your answer is the solution set 12.
All right, my brain hurts. I'm not doing it anymore. Bye.
Shane, that's perfect. All right, someone else. Part D. You can do this. Melina, can you walk us through part D?
I can try.
Cool. What would you do first?
Do we take the -2 and bring it to the other side?
Beautiful. So she's isolating the radical. So we got cube root of 1 minus 2x is equal to 3.
So do we take, do we multiply by the cube?
Yes. You mean raised to the power of the cube? Yes.
Yeah.
Yes. So what Melina noticed here is that we have the cube root this time. So in order to cancel the cube root, you have to raise it to the 3rd power. Yes. So what does that result in?
1 minus 2x equals, was that, I don't know what that is.
27.
12?
I'll be your calculator.
27. Okay.
And then we solve. Cool. Let's solve this. Easy peasy. What do we do next?
subtract the 1.
Beautiful. Negative 2x is equal to 26.
And then divide the -2.
Yeah, look how cool that ended up being. It wasn't even too crazy. It was just the idea of, oh, snap, now I got to raise to the third power, not to the second power, right? Because it's a cube root. Always double check. So we have, and I'm just going to write it out here since I have a little over 60 seconds left of class. So we have to do our check. We've got the cube root of, and then 1 minus 2 times the -13. So 1 minus 2 times the -13. Let's try this one. Oh my God. 1 minus 2 times -13 is going to give me 27. And then minus 2 is equal to 1. The cube root of 27 is 3. Okay, it worked. Yes. So my answer is the solution set, -13. And we're done. How does my brother always call me while I'm teaching? Perfect. Very, very, very nice. Keep practicing these. Let's take a look at your Lumen because we need to assign some homework and I want to do that with you. Let's check it out. So we have unit 3 stuff to do. Let's go to that. He's calling again. Okay. Unit 3 homework. And we do have a lot of different concepts, but we actually covered literally everything up to and including solve radical equations. The last thing we have to do in tomorrow's class is complex numbers. I would advise you to print unit 4 notes as well for tomorrow's class. Okay, so definitely do that. Let's come up with some due dates for these guys. What would be a good due date for these assignments?
How about the first 3? We can have them do, so exponents through simplifying rational, we can have them do Wednesday. Simplifying advanced through dividing radicals, how about Friday? And then higher order through complex do Sunday.
Ooh, what do you all think of that?
All right with that.
I don't know about all of that.
Okay, tell me, give me some ideas. Give me some ideas. We're talking about, let me look at them real fast. Unit 3 homework, here they are. So yeah, talk to me. Give me a different scheme if you'd like something different. I'm just going to open these up.
A lot of homework.
It is. They're not a lot of problems, I promise. They're really not. So give me suggestions. Shane gave me a suggestion. We had someone said that that's cool with them. Give me a different suggestion.
Could we just have them all due on Friday and that way we can work at our own pace to it? If some people have a hard time getting through the first 3 before Wednesday.
That's true. That's true.
I was gonna say all by Sunday.
Oh, all by Sunday? Would everyone be comfortable with all by Sunday?
Cool beans.
I can go to
Yes.
Okay. Let's do that. Copy down dates and times. Oops, cancel. I gotta actually select them real fast. So I'm going to copy this down. Due Sunday is totally fine with me. I think that's definitely reasonable. So let me copy down dates and times. Perfect. These are all due by the 27th, 11:59 p.m. So please don't let these sit by the wayside. Make sure you're doing a little bit every day. What I will suggest is what Shane suggested to you all. Like maybe you do the first 3 by Wednesday and then the next 3 by Friday and then the rest by Sunday. That's a good way to manage your work and manage your time. Think about doing that. But yes, I'll have them all due by Sunday in case you're working or have other obligations. Okay. I'll see you all tomorrow. Make sure you print unit 4 notes.
Professor, you have time after class?
Yeah, I'm staying.
Okay, thank you.
You're welcome. Bye, everyone.
All right, we'll
Thank
talk
you.
about it, Professor.